fellow embedded heads. In this video, I'm going to show you how you can debug and trace Zephyr applications on Arm Cortex-M based MCUs using the SEGGER Ozone debugger in combination with SEGGER Debug and Trace probes. For links and hints, please see the description below. If you're enjoying this video, please like and subscribe. Let's get started. First, let's review what a typical Zephyr development environment looks like. Typically, you're developing your Zephyr application using some integrated development environment or via Microsoft Visual Studio Code with some specific extensions, or simply using the West Meta tool for Zephyr. Your Zephyr project most likely has a configuration file called prj.conf, which we're going to talk about in more detail later on. Whenever you build your Zephyr code, you're invoking a toolchain of your choice that supports your target MCU. This typically results in an executable ELF file that also includes all required debug information. You can then open that ELF file with SEGGER Ozone and debug your project on your target board using a SEGGER J-Link or J-Trace probe. Ozone is a powerful standalone graphical debugger from SEGGER that offers RTOS awareness for Zephyr and is included with most SEGGER Debug and Trace probes. You can download Ozone from the SEGGER website under Downloads, Ozone. In order to do Zephyr RTOS-aware debugging in Ozone, it is important to add a couple of kconfig settings to the configuration file in your Zephyr project. With these settings, Ozone can show Zephyr thread information. Ideally, if your circumstances allow, also build your project without any optimizations for the best debugging experience. Another important step we need to take is to enable the Zephyr RTOS awareness in Ozone by loading the Zephyr RTOS awareness plugin. For this tutorial video, I'm using an NXP MCXN947 Freedom Board that is connected to my PC via a SEGGER J-Link. As my Zephyr development environment, I'm using the NXP MCUXpresso extension for VS Code, and I'll be working with the threads example from the Zephyr repository. After updating your project configuration file as mentioned earlier, rebuild your Zephyr project in whatever development environment you're working with. Then open SEGGER Ozone and create a new project for the MCU on your target board. In my case, this is the NXP MCXN947, CPU 0 of that device to be exact. To see the peripheral registers, you can also load the matching SVD file. Next, configure your target interface settings and select the SEGGER probe you're using. Finally, point Ozone to the ELF file for your Zephyr project and finish the project creation process. Ozone loads the ELF file and opens the C file with the ELF entry point. Make sure to enable the Zephyr RTOS awareness by loading the Zephyr RTOS awareness plugin via the Ozone console window. By the way, you're going to want to keep an eye on the console window for messages from Ozone during debugging. Now you can start your Ozone debug session by clicking the green Start button. Ozone loads the project into the target MCU via the connected J-Link and halts at main, or in this case, a weak implementation of main. You can now step through your source code, step through your assembly code, or simply run your project. Whenever you halt code execution, Ozone allows you to examine the Zephyr threads that have been created by your project in the RTOS window and see their task IDs, priorities, status, and stack information. Double-clicking on individual threads loads the associated stack frame for additional visibility. Via the source file window, you can open and examine additional files like main.c in this example. Here you can see where the 3 Zephyr threads are being created. You can set breakpoints to control code execution, for example in the function that controls the blinking of the LEDs for threads blink0 and blink1 in this example. All code, data, and trace breakpoints can be seen in the break and trace point window. Hover over variables to see their current value, their type, size, and other important information. Double-click variables or expressions and drag them into a watched data window, set a refresh rate, and see them change in real time. Drag variables or expressions into the data sampling window to graph them in the data pane of the timeline window while your application is running. The global data and local data windows let you inspect all global and local variables in one spot whenever code execution is halted. You can also examine and modify all core, system, and peripheral registers in the Registers window, which you can have multiple instances of. If you need to inspect memory, Ozone offers a special memory usage window which shows memory segments, data sections, and debug symbols in an interactive graphical memory map. You can look for addresses, address ranges, symbols, or even expressions. For example, let's find the main function. You can now show its source code, its data, and even set a breakpoint on it. You can also scroll up and down in the memory map, as well as zoom in and out anywhere you like. The call graph window provides important information on function call paths and stack usages. If your target device has an embedded trace buffer, you can select it as the trace source in the trace settings. Make sure the CPU frequency matches your settings. Now, when you halt code execution or stop at a breakpoint, the instruction trace window shows us the history of what has been executed. The most recent instruction executed is shown at the bottom. You can navigate through the instructions to see what happened on the target before we hit the breakpoint. The source viewer, the disassembly window, and the timeline window are all synchronized with the selected instruction. Instructions are grouped by their source function. We can collapse them to see a source function level backtrace, or expand them to know exactly which C and assembly instructions have been executed. The code pane in the timeline window provides a graphical representation of the call stack over time. The timeline is based on recorded trace data mapped to the source function information. The code profile window visualizes the code coverage and code profiling information by source function. Sort by source coverage to check how many lines of each function have been executed, or sort the functions by assembly instruction coverage. The run count shows how often each function has been called. The load gives information about where the time is spent in the application. The data shown is the data that got recorded since the trace data has last been cleared. In the timeline window, you can select if you would like Ozone to clear the trace data each time you resume code execution, each time you reset code execution, or never. When tracing via the embedded trace buffer, it is best to clear the trace data every time you resume code execution. Because the data pane and the code pane are located in the same timeline, you can see the correlation between your graphed variables and the executed code. Notice that there's also a power pane that lets you correlate current consumption with your graphed variables and the executed code. However, you need to power your target board via the SEGGER probe in order to take advantage of this feature. Tracing using the on-chip trace buffer can certainly be helpful, but due to the small size of the trace buffer, usually only a few kilobytes, the amount of trace data that can be recorded is also quite limited. If your target device and your target board support tracing via dedicated trace pins, it is much better to get a SEGGER J-Trace streaming trace probe and connect to your target that way. Using the on-chip embedded trace module in combination with a SEGGER J-Trace gives you the full benefits of tracing, like a virtually unlimited trace buffer, as well as live code coverage and live code profiling. When you're done with your debug session, make sure to save the Ozone project so you can pick up where you left off when doing your next session. Note that you can also edit the Ozone project file, for example, to add the loading of the Zephyr RTOS Awareness plugin, so you don't have to do this manually every time. And there you have it, fellow embedded heads. Now you know how to debug and trace your Zephyr applications using the powerful SEGGER Ozone debugger in combination with SEGGER J-Link and J-Trace probes. If you enjoyed this video, please like and subscribe. Please also feel free to leave comments below. Thanks for watching.